All right. Hello, folks. We're going to quickly talk about chapter 7, which is pathophysiology. One thing to remember here is that this chapter is all about kind of what happens when things go wrong in the body. For example, if the heart's not working correctly, and then how the body compensates for that. We have this very small space that we live in. That's where our bodies try to achieve what's called homeostasis. It's kind of like the Goldilocks zone, right? Like the porridge is not too hot, it's not too cold, it's just right. And the body's always trying to keep itself in there. So when things go wrong, we go off to the side a little bit where things might be not right, and the body compensates, uses predictable mechanisms to get back to where that homeostasis is, that Goldilocks zone there. So keep that in mind. It's all about being in the right balance with things throughout this chapter. All right, so pathophysiology, it's the study of how diseases, and it's not just diseases, but how like trauma can affect the body as well. So what happens negatively to the body and how the body responds. Understanding pathophysiology in this way helps us to recognize what's going on in the patient and what we can do to help them. So it's important to recognize and to be able to think through what is happening in the body, what the body will do to respond to it, and how those changes affect the patient. And if we understand that, then our pathway to good patient care is much more clear, because we're going to be given basically road signs on what to do with these people and caring for them. All right. So there's a bunch of stuff in this about the cell in this chapter, and really what we need to know is about the cell is that they're constantly making energy, ATP. It's called adenosine triphosphate. We know that, and in order to make energy, it needs three things: it needs enough water, it needs enough oxygen, and it needs enough glucose. Without those three things, then we start to have problems. Or if the balance of those three things is incorrect, then we start to have problems. In studying for this test, you don't need to learn about all of these things, right? I'm not going to ask you any questions about the specific structures of the cell, because you'll never be on an ambulance thinking, I wonder what's wrong with their rough ER or the rough endoplasmic reticulum. Okay, you're never going to ask that. So while you've read it and it's good to understand it, there are not going to be any questions on that. Now back to here for one quick second. Again, cells are always trying to make energy to stay alive, to do their processes and their jobs, and without proper ATP, they can't function correctly. And so that means without enough oxygen, they can't make enough ATP to function well. So not enough oxygen, they don't function well. Not enough glucose, they don't function well, etc. So the important thing to know about the cells, again, is that it needs water, glucose, and oxygen. And without those things, they can't make energy and they can't do their jobs. They can't do their jobs. Eventually, they're going to die. That's what we need to know about the cells. All right, so let's talk about the three things that I just mentioned: water, glucose, and oxygen for the cell. So for the cell, we need the correct amount of water inside and outside the cell. If the cell doesn't have enough water inside, it dehydrates and it dies. If there's too much water, um, things get watered down basically in the cell, and there's not the right mix of things, and so the cellular function is disrupted. Cells can even burst. They fill up too much with water and they can burst and die. Obviously, it's like putting a water balloon on a spigot and you just turn it on and just let it fill up until it explodes. So if there's too much water, can't do its job. Too little water also can't do its job. And both can end up with the death of the cell as a result. Now, there are things called electrolytes in our bodies, and these help with muscle function, or just about everything that has to do with electricity in our body. So we need things like sodium and magnesium, and et cetera, to help with our muscle functions. Um, these things, electrolytes, they dissolve in water, and then they help inside the cells to do their jobs. There, too much water, the electrolytes get watered down. It's like if you make sweet tea, and the regular recipe calls for 1 cup of sugar in a gallon of water. That's right, it makes it just sweet enough. But if you up that water content but keep the sugar the same, like if it's 10 gallons of water with 1 cup of sugar in it, like you're not going to taste that sugar at all. It's completely watered down, and it's not doing its job. And that's exactly the same thing that's happening with the electrolytes there. There has to be the right water balance in there. Too much, and they can't do their job. Glucose, it's a building block for energy. Every cell needs it. Without it, they can't make energy. And then soon enough, their functions are impaired. They can't do their jobs well, and then they die. So obviously, we need a right amount of glucose in the cells. Now, in order to get glucose in the cells, we need insulin. We've talked about this, right? It's a hormone made in the pancreas. So the glucose amount has to be just right, and so does the insulin amount. If there's too much insulin, then all that sugar is burned off very quickly, and then all of a sudden there's no sugar left for the cells. If there's not enough insulin and but the right amount of sugar, then we can't get that sugar into the cells if there's not enough insulin, and then soon enough the cells are functioning inadequately without that sugar because they can't make energy. Their functions are impaired, and then they die. So got to have the right amount of sugar, right amount of insulin for things to work. Oxygen in the cell, we know about aerobic metabolism. This is the normal way that cells make energy. They use oxygen with the glucose to make that ATP, so they can do their work. They can do all the jobs that those cells need to do. Now, when there's a lack of oxygen or an inadequate amount of oxygen, our cells go into anaerobic metabolism. So they're trying to make energy without or with very little oxygen. Now, a result of this, as we know, is it makes much less energy, and it makes a lot more waste, a lot more carbon dioxide, a lot more lactic acid. And this is a problem. We have too much waste products being made. The blood and the body become acidic, and it impairs functions. One of the bigger functions that it impairs is red blood cells' ability to carry oxygen. Red blood cells do not like an acidic environment. It affects the hemoglobin, which is the part of the red blood cell that actually carries the oxygen. And so the more acidic the blood gets, right, the more carbon dioxide, the more lactic acid that's released from the cell. The more that happens, the less oxygen your body is carrying. The red blood cells just hate that environment, and they can't do their job well. And so unless that aerobic metabolism gets switched back somehow to, so if that anaerobic metabolism can somehow get switched back to aerobic, things go back to normal. If that doesn't happen, then we have a vicious cycle here. So we have a lack of oxygen that makes them go into anaerobic metabolism. The body gets acidic because of all the carbon dioxide and lactic acid, et cetera, that's in there. And it just becomes a vicious cycle, right? So with the blood not being able to carry oxygen. So we have poor oxygen, which results in higher waste products, which results in less oxygen being able to be carried. And it's just a vicious cycle. It goes on and on and on until things ultimately get so bad that the patient goes into shock and then dies. So obviously we want to correct that before this happens, or before we're in this state for too long. We need to know the definitions of both. We learned those last chapter, but we still need to maintain those and understand what's going on. All right, so one thing that we need to know is what's called permeability. Um, for lack of a better term, permeability is how leaky things are. So that could be a cell, or that could be like the walls of capillaries, our smallest blood vessels. Now, some of it is good. Some things can go in and out of the cell normally. Okay, like water diffuses across the cell, certain substances go in and out, things like that, and that's good and that's normal. So we want a certain amount of leakiness, but if it's too much leakiness, then too much water gets in. Things that aren't supposed to be going into cells, or too much of those things are getting into the cells, or our capillaries are leaking out too many fluids, too many things like that. So um, permeability is a good thing. Too much of it is a bad thing. I guess like most things in life, right? Um, so a cell membrane, if it's ineffective, it can allow substances in that cell that shouldn't be there, or too much of substances as well. If there's too much of things that aren't supposed to be in there, then it takes up space that water should be taking up in there. And so it can interfere with that regulation of the water. All right, let's talk about the cardiopulmonary system. It's the respiratory and cardiovascular systems working together. We've talked about this a lot, and so we can see that the dynamic between them, how closely they have to work with each other. One system can't function without the other. They have a symbiotic relationship. They support each other. So we know the three jobs there. The cardiopulmonary system, we bring in oxygen, right, from the outside world into the body. We remove waste products, and then that oxygen is being delivered to the cell, while the waste products are taken from the cells and out of the body. Any breakdown here, so if we can't bring in oxygen, if we can't get it to the cells, or if we can't remove the waste products, any breakdown, we can result in system failure, which is basically that means cells aren't functioning correctly and then they die. All right, we know the parts of the airway. The upper airway is everything above the cricoid cartilage, and the lower airway is everything below the cricoid cartilage there. And then we know our alveoli, our bronchioles, wrapped in smooth muscles. We know about this. All right, here's a definition that we need to know. That's called patent, right? Every patient, every person needs a patent airway for the system to function. That means that we're open, the airway is open from top to bottom. Right? Air is not being impeded on the way down by an obstruction. And that could be a foreign body, somebody chokes on a piece of food, a kid eats a Lego, or what have you there. So a patent airway is something that all patients need. Upper airway obstructions are common, right? This is when people are choking on things. Again, it's a piece of food, it's a toddler eating a marble, Legos, some kind of toy, a piece of hot dog, whatever they might be. So upper airway obstructions are more common than lower airway obstructions. And they can be caused by, again, foreign bodies, infections. Your airway can swell and close. Trauma can produce that. Fluids like vomit or blood, things like that can become obstructions in the airway. Again, we got to know the definition of patent. Lungs, we know about these, part of the lower airway. And one thing we have to know is what's called tidal volume. This is the amount of air moving in and out of the lungs with each breath cycle. So it's a certain amount of air. It's a volume of air. Now, what we need to know here about tidal volume is basically that it's 500 milliliters. All right, it's about a bottle of water, basically, just about 500 milliliters there. Now, not all of that is air that reaches our alveoli. There's something that's called dead air space, and on an adult, it averages about 150 milliliters. But there's air when you take a breath in the middle of your trachea or in your bronchioles, but that doesn't get all the way down to your alveoli. We don't actually use that air. It's brought in, but it doesn't get to the places where the gas exchange takes place. And that's called dead air space. And again, that's about 150 milliliters. Now, there's a concept that we have to know. It's called minute volume. And to calculate our minute volume, as you can see here, we take the tidal volume, how much air somebody brings in, times their respiratory rate, and that gives us our minute volume. That's how much air is brought into the body in 1 minute. Now, it's important to understand this because everything about breathing problems either affects the tidal volume, the respiratory rate, or both. Every breathing problem, it's either a problem with the tidal volume or the respiratory rate, or it can be both. And that's going to affect their minute volume there. So we need to know what tidal volume is. We need to understand what minute volume is and how they're affected. So I can lower the tidal volume. Let's say somebody has asthma, and instead of bringing in 500 milliliters, they're bringing in 350 milliliters. And you times that by the respiratory rate. Let's just use a simple number, right? So let's start with normal. So if tidal volume is 500 milliliters normally, and let's just say they're breathing at 10 times per minute, just to make the math simple. The minute volume there would be 5,000 milliliters, right? 500 times 10, 5,000 milliliters, right? That would be normal for an adult. Now let's again say they have asthma and their bronchioles constrict because of the smooth muscles constricting around the bronchioles. So that reduces the tidal volume. So that is going to affect how much air is brought in over a minute. So let's say the tidal volume with an asthma patient is reduced to 350 milliliters, times that by the same respiratory rate. Again, just to make the math simple, times that by 10 breaths per minute, that is 3,500 milliliters. So that's much less than the 5,000 that we bring in normally. So if we affect respiratory rate or tidal volume, we can mess with our minute volume, bringing it up or down. So if there's a problem with either one of those, respiratory rate or tidal volume, then it's going to affect how much air we bring in over a minute. There you go, just like we said. All right. So anytime we have respiratory system dysfunction, we're messing with our minute volume, okay? And again, change tidal volume or change respiratory rate, and we can have effect there on the minute volume. All right, this is about how we affect breathing. There's 3 ways to affect our breathing here. The first way is to disrupt respiratory control. What does that mean? It means that there is an effect being placed on the part of the brain that controls our breathing. It's basically the control center for our breathing, and that's called the medulla oblongata. This can be affected by many things, including drugs, infections, toxins, trauma. If you have a stroke in the right place in your brain and whatever artery is feeding the medulla oblongata with blood, if that's blocked off, then all of a sudden the medulla oblongata can't be working right, and then we'll have effects on breathing changes. Opiate users, for example, when they overdose, the medulla oblongata is basically told by the drug that, we're good, we don't need to breathe. And so you'll see somebody who overdoses on opiates, you'll see their respiratory rate steadily decline until it stops. And that's how they die, people who overdose on opiates. And it's the effect that the drug is having on the medulla oblongata. So if there's trauma to the brain, toxins, drugs, infections, things like that, that can affect our minute volume by affecting our breathing rate and even the respiratory pattern. We have this nice, easy pattern: in, out, in, out, in, out, usually drawing in and exhaling the same amount of breath. It's not too shallow, it's not too fast, it's just kind of right. Again, that Goldilocks zone, and then we can affect the pattern. Maybe it's very quick, very quick, very quick, and then maybe it stops. Maybe it's very slow and it's irregular. Things like that. So breathing patterns can also come into play here when the medulla oblongata is affected. So first part of respiratory dysfunction is disrupting the control center for breathing, the medulla oblongata. Here it is. You can see it right down there. It's at the bottom of the brain stem, right basically where the spinal cord is coming out of the brain, right there, as we've seen. Second way to disrupt respiratory function is to disrupt the pressure. So what this means is that there's going to be either a problem A with the chest wall itself, or B, we have like rib fractures or punctures in the lungs or something like that. Now, if you'll remember back to chapter 6, when we talked about the pressure inside of the chest, when our chest expands, our ribs go out and up, our diaphragm drops down, it creates a negative pressure inside our chest as the space is increased, and it draws air in. When our rib cage, when our muscles, our intercostal muscles and our diaphragm relax and our rib cage shrinks back down, it creates a higher pressure and it forces the air out of our system. Obviously, we know that's how we take a breath. So if we compromise the system that does that, right, the chest wall or all the muscles or the lungs themselves, we have a disruption in pressure. This can lead to air and sometimes blood accumulating in the pleural space, and this can compromise our respiration. So, examples of this: let's say your patient was in a motor vehicle accident, not wearing their seatbelt, they got bounced around in there and they broke a bunch of ribs. Well, that's going to be incredibly painful just to take a breath if they've got lots of fractured ribs. And so maybe they're not taking as many breaths and they're taking very shallow breaths, right? Well, we're not able to use the pressure that we can generate with our chest because of that. And so that's going to affect the pressure in there. It's going to affect how much air they can breathe in, and that's going to affect their minute volume. Another thing that we can do, a patient can happen to a patient, is if they've been shot, stabbed, or had a rib puncture a lung, and when they breathe out, every time they breathe out, air will escape that lung into the pleural space, or blood as well. And the more they breathe out, the more air that's surrounding the lung, and eventually it kind of crushes it and collapses it. So that lung is no longer accessible for gas exchange. So that will definitely affect your minute volume if you only have one lung able to bring in air. And eventually that's going to affect the other one as well. So any disruption of pressure, either messing with the chest wall, right, rib fractures, a hole in the chest wall, things like that, or affecting the integrity of the lung tissue itself, putting a hole in it can disrupt the pressure. So that's the second way we can disrupt respiratory function. The third way is disruption of lung tissue itself. So if it's been shot, stabbed, some way disrupted through trauma, right? We can't, or medical conditions. It compromises our ability to get oxygen to the alveoli so the gas exchange can take place. So for example, folks with COPD, they can, after years and years of smoking, they can essentially make their alveoli non-functional. And so the lung tissue has been disrupted. The air can get down there, but there's nothing there. The alveoli aren't there to work because of all the smoking they've done. They don't work. And so the gas exchange isn't taking place. And that obviously is going to affect our minute volume. Less oxygen gets in as a result, less carbon dioxide gets out. So that just becomes a vicious cycle too over time. Here's a couple definitions that we need to know. Low oxygen levels in the body is called hypoxia. Hypoxia. If we remember, we watched that video in class. If you weren't in class, I'll link it in our Canvas. There are the hypoxia videos. And we can see in those videos cellular dysfunction. Well, cells in the brain anyway, we can see how their thinking is affected. It's a good videos to watch. Again, I'll link them in our Canvas there, and we can apply the lessons there of how one type of cells, brain cells, are affected by low oxygen levels, and kind of take that lesson and apply it to the rest of the body. And because it's hard to say, hey, you don't have enough oxygen and cells don't do their job, and then eventually they die. So it's kind of hard to see that, but in these videos we can see how brain function, specifically thought, is disrupted with low oxygen, and we can kind of apply those lessons across the body. So hypoxia and hypercapnia. We need to know those two different definitions. So what happens when there's respiratory dysfunction? What happens there? Well, if our minute volume is affected because of some sort of dysfunction, right? We mess with the control center in the brain, we mess with the lung tissue itself, we disrupt the pressure somehow. Our body is going to try to compensate for the lack of gas exchange. That's happening there. We're going to try to bring on more oxygen, and we're going to try to get rid of more carbon dioxide. We're going to attempt, our body's going to attempt to manage the deficits in our minute volume. So in our blood, what we have, or in our blood, in different places in our bodies, we have these things called chemoreceptors, and they detect oxygen and carbon dioxide levels in our bloodstream. So we have some that are in our aortic arch, we have some in our carotid arteries, we have some in our brain, and they're just basically data collection centers that are just testing the blood to see how much carbon dioxide and how much oxygen is in there. In a normal healthy person, they normally detect the carbon dioxide levels first. So they say, hey, we've got too much carbon dioxide level, or carbon dioxide levels are too high in the blood. So they tell the brain, the medulla oblongata, like, hey, there's too much carbon dioxide here. We need something to get done. So the medulla oblongata says, okay, I understand. Let's make the body breathe a little bit deeper and a little bit faster. That way we can bring in more oxygen and we can get carbon dioxide out of the body. So that's how they start to compensate. That's one way they start to compensate. The brain is told, hey, there's too many levels of this, the carbon dioxide, we're getting too acidic. Let's breathe some more. Let's breathe faster. Let's breathe deeper. So we can up our minute volume and we can make up for whatever dysfunction there is. And we need to know about chemoreceptors and what they measure. All right, the blood, we know about blood. We'll talk about blood dysfunction here for a second. We know about the 4 parts and their jobs. Learned that last chapter. We need to know about this. This is basically water balance. This is about water balance here, this part in the blood, which is important to know. The first thing we have is what's called plasma oncotic pressure. We have large proteins floating through the blood. And what they do is as they're going down the bloodstream, they attract water that's outside the bloodstream. It's around the cells. Basically, it's next to the bloodstream. It's around the cells. And as they pass down through the bloodstream, it draws water from outside the bloodstream, from around the cells into the bloodstream. Okay. It helps keep the bloodstream hydrated. It helps with our water and fluid balance there. And so it's very helpful. However, if just this process was in place, we would eventually dehydrate the cells because we're taking water away from the cells. And so in order for this to work well, plasma oncotic pressure, we have to have an opposite, kind of an equal and opposite reaction that's putting water back towards the cells. We can't just take it away from the cells. We have to be able to put water back there as well. And so at the same time that plasma oncotic pressure is happening, which is happening all the time, we have what's called hydrostatic pressure happening as well. This is the opposite process. This takes and pushes water from the bloodstream out to the cells. So these things are working kind of against each other at the same time to maintain a fluid balance in the blood and around the cells. So what hydrostatic pressure does is that pulse wave comes down there, it actually pushes water, it helps force water out of the bloodstream and into the cells. So both of these things are happening at the same time. One's taking water a little bit away from the cells and one's pushing it back. So there's a nice balance, that Goldilocks zone of enough water in the blood and enough water around the cells. If either one of these things isn't working right, we're going to see problems. We're going to see problems. For example, if somebody has liver failure and they're not making a large protein called albumin, it's a large protein, it attracts a lot of water from around the cells. If they're not making that and the water is not being brought out from around the cells, then it's going to stay there. And what we're going to see is called edema. We're going to see water being in gravity-dependent places. So wherever gravity can get a hold of water and drag it down. So you're going to see swelling around the feet and ankles, the lower legs. You're going to see it below the elbows and around the wrists and hands, things like that. It's mostly in the legs that we see it, but you can see it in the hands as well. Their forearms, wrists, around that area. So again, if the plasma is not there because of liver failure, then we're going to start to see swelling in places because the water's just getting pushed out towards the cell. So we have a fluid balance problem. Right? So we need to know what each of these is, how they work with each other, but kind of against each other to maintain that nice Goldilocks zone for fluid balance there in the blood and around the cells. Well, that's fancy. All right, with blood dysfunction, obviously without enough blood, then we can't carry oxygen down to the cells and we can't remove the waste products as well. So that's a big problem. So there's a list of a few types of blood dysfunction. So if we bleed out a lot, obviously every drop of blood that we lose a little bit of the ability to carry oxygen and to remove waste products. Right? If we don't have the red blood cells there to carry the oxygen, well, then we can't do it. If the plasma is not there to have carbon dioxide dissolve into, well, then we can't do that. Can't remove the waste products. If we get severely dehydrated, the blood gets dehydrated as well and can't do its jobs there. Anemia, it's a lack of good red blood cells to carry oxygen. That's a problem. Liver failure is a problem. The liver, as we know, detoxifies and cleans the blood. And if that environment is allowed to become highly acidic, then as we know, then we're not being able to carry enough oxygen around. So all of these things can lead to blood dysfunction. Here's the blood vessels. We know all about those. All right, so we know about the blood vessels. We know this whole process here that take blood from the lungs to the heart, to the body, and back around again. We know all about that from last chapter. So the blood vessels in order for the blood to be properly circulated, right? As we learned in CPR, there's needs adequate pressure to work. Okay, what this means, it's like taking a Windex bottle. You squeeze it 4, 5, 6 times before it squirts. Well, what you're doing when you're pumping it up 4, 5, 6 times before it actually squirts is that you're building the pressure in that little system between the pump and the little straw going down into the fluid there, the Windex. You're building up the pressure to actually make it work. Our body is the exact same way. If we don't have the heart pumping to build up that pressure and push it around, the blood doesn't go around. So we need an adequate amount of pressure in there, and the blood vessels help with that. The blood vessels help control blood pressure by constricting or dilating as appropriate. Now, how does that happen? Well, we have these things called stretch receptors in our arteries, and they monitor pressure. So if they see our pressure is falling, the stretch receptors, these data collection centers, kind of like the chemoreceptors, they tell the brain, hey, our blood pressure is getting a little low, and so the brain tells the blood vessels to constrict. When blood vessels constrict, the blood pressure will go up. When the blood vessels dilate, get bigger, blood pressure will go down. Now, this is a process that's happening all the time as you speak. As you're watching this right now, it's happening. If you're sitting down, the next time you stand up, your blood vessels are going to contract a little bit to help keep blood going to your head, right? It's happening all the time. Obviously we don't notice, we don't control these things consciously, but it's happening all the time to monitor our pressure. So depending on the situation, like I said, it can be increased or decreased depending on what the body needs at that moment. So we can have a couple ways to have blood vessel dysfunction. One is called loss of tone. Right, now we've talked about this loss of tone. We talked about it in CPR and opening airways, right, airway management, things like that. So loss of tone here basically means that the vessels lose the ability to control their muscles, right? So they can't constrict, excuse me, or dilate. Because of this, they're just kind of blown wide open. They're just all the way wide open, and so the pressure drops precipitously. It can be dangerous. It can be life threatening. It can kill a person if they have loss of tone. Causes for this can be trauma, infections, and allergic reactions there. So loss of tone, the loss of the ability to control their diameter, whether they're small or big. That when that happens, our body loses the ability to control our blood pressure via this route. Um, so it's not a good thing. Not a good thing. So loss of tone, basically loss of muscle use in the blood vessels. All right, so on the left, we see a normal blood vessel filled with blood. It's constricted a little bit, and doing that helps the blood to flow, right? On the right, we see a blood vessel that has a loss of tone, right? Same amount of blood in there. But we can see how much bigger the blood vessel is. When this happens, like we said, the blood pressure drops precipitously. It's not a good thing, really bad. When the blood pressure is going to drop like that, the blood is just not going to flow well. Essentially, this is like when you turn on a garden hose, right? You don't have it's just pouring out of the end. It's pouring out. It's not shooting out or anything else. It's just kind of pouring out of the end like that. It's going just not real well. But when you put your thumb on the end and you make that opening, you make it smaller, the opening, you can even feel the pressure building up against your thumb, and you're making that water eject from the hose at a much greater distance, right? What you've essentially done is you've constricted it, at that one point and made the pressure higher. And so it flows better. Now, if you take your thumb off of that hose at the same time, it goes back to being the blood vessel here that we see on the right-hand side. It's just kind of pouring out. It's not being injected through the hose there. So another way we can have blood vessel dysfunction is excessive permeability. The capillaries leak fluid out of their walls. So again, we said permeability is like the level of leakiness that we have from cells or blood vessels to capillaries. And a certain amount of it is good, that we like, okay? But when it gets too much, then we have a problem. We can have severe infections that cause it, high altitude, certain diseases, trauma, things like that. That can affect it. So too much is bad. We're going to be leaking fluid all over the place, and you're going to see the effects of that with edema. And the last one is hypertension, high blood pressure. We need to know what hypertension is. Hypertension produces something called systemic vascular resistance. What that is essentially how hard the heart has to push against the pressure inside the vessels. SVR is the pressure inside the vessels. The higher your blood pressure goes up, the more SVR you have, the more systemic vascular resistance that you have. And that means the heart has to work really hard to push that through. Now, the blood vessels don't like being in a state of hypertension. They have to hold all that pressure in there. Eventually it weakens, and we can have things like aneurysms, strokes, where a blood vessel bursts because it just can't handle the pressure over long periods of time. Hypertension causes lots of problems, including heart disease there. So it's a major risk factor for stroke and heart disease. So we can literally blow up some of our blood vessels from having too high of a blood pressure for too long. There again, it causes a lot of strokes, things like that. All right, let's talk about the heart. All right, something we need to know is called stroke volume. This is how much blood is ejected from the heart every time it beats. So average for an adult is about 70 milliliters, which is not a large amount. But when you take that out over a minute, you get obviously a lot of blood going around the body. So the stroke volume, how much blood is put out with each heartbeat, was predicated on a few things. One is called preload. Preload is just how much blood has been returned to the heart. So if it's normal, it'll fill up with the normal amount. If it's somehow short, then the stroke volume will be less as well. Contractility, it's also based on that, and that's how hard the heart squeezes, how hard it beats. Okay, if you've ever felt your heart pounding, then your contractility in that moment was up. Right? So the harder it squeezes, the more it can push out. And then there's something called afterload. Now, this is important to know. People get this messed up every time, every EMT class. Afterload, what people think is that it is stroke volume, how much blood the heart puts out, and that's what it sounds like. They should have called it something different. But what afterload is basically it's the systemic vascular resistance. It's how hard the heart has to push to actually overcome the pressure in the vessels to actually push the blood out there. Okay, how hard the heart has to work there. So the higher your patient's hypertension is, the harder it is going to be for the heart to actually push the blood out there. If it's too high, it's not going to be able to push as much blood, and so your stroke volume will go down. So important to remember, afterload is basically systemic vascular resistance. Okay, it is not the amount of blood that comes out. That is stroke volume. All right, cardiac output, much like minute volume, it's how much how much blood our heart is ejecting per minute, and we can figure that out with when we do stroke volume times beats per minute, and that's how much blood per minute is going around the body. So it's important to know that as well. So either slowing the heart rate or decreasing the stroke volume, that's going to reduce the amount of blood we put out with each heartbeat, or over a minute rather. So slowing the heart rate or decreasing stroke volume reduces how much blood is ejected from the heart per minute. Now, it's not just decreasing stroke volume the heart rate that can reduce cardiac output. If the heart is beating too quickly, there's a point where there's diminishing returns. There's a point of diminishing returns when the heart is beating quickly. If it starts to beat too fast, then it won't be able to fill up with blood as much as is normal before the heart beats. There's just an inadequate amount of time to fill that left ventricle with enough blood to be pumped out, just because it's beating too quickly. So at a certain point, heart rates, when they're too fast, there's diminishing returns there. So we need to know how we calculate cardiac output. All right, so heart dysfunction. We've got a couple ways that we can have heart dysfunction. One is mechanical problems. This is a problem with the actual physical heartbeat, the actual squeezing in the heartbeat. Okay, there's mechanical problems, and that can be caused by trauma, squeezing forces. You can have a heart attack, which results in cell and muscle death of the heart. So if somebody has a heart attack in their left ventricle that's particularly large, maybe their cardiac output drops by a large amount because the left ventricle simply just can't pump the blood out enough because too much of its muscle has died. We can also have electrical problems. Now, if you remember, we went over the whole electrical conduction system, cardiac conduction system there. So if we have problems, say, with the SA node or the AV node, or we have problems with the nice, orderly, organized pathways in which the electricity flows throughout the heart to get that nice organized beat. we can have problems there. So we might have rate problems. Maybe the heart's beating too slow. Let's say the SA node and AV node have both stopped functioning. Well, then we're going to be beating somewhere between 20 and 40 beats per minute if that's the case. And that's pretty slow. That's real slow. So obviously our cardiac output is going to be affected there. We can also have electrical problems that cause our heart to beat too quickly. So again, our cardiac output is going to go down if the heart doesn't have enough time to refill between beats because the heart is beating too quickly. So two problems with the heart that we can have are either mechanical problems, there's a problem with the beat itself, or there's an electrical problem as well. So putting it all together, the whole cardiopulmonary system's got to be working together in conjunction with each other to work just right, to keep us in that Goldilocks zone of enough minute volume, our cardiac output, keeping it at those right levels. And having those two things in balance is called a VQ match, okay? Ventilation is the V, and the Q is perfusion, obviously. They got to use Q for perfusion. Ventilation has got to be right, and the perfusion has got to be right. We've got to bring in enough air and get enough waste products off board there. And we still have to have the ability to circulate that oxygen and circulate the carbon dioxide to get it back to the lungs to get it out of the body. So if there's a problem with either one of those things, we have what's called a VQ mismatch. Now, if we have these problems for long enough, obviously it can cause a life-threatening condition. All right, let's talk about shock or hypoperfusion. What we're going to talk about here is 4 general categories of shock or hypoperfusion. And later we have a chapter on shock all by itself, and we'll be able to fit different kinds. We'll be able to slot them in, these different kinds of shock, into these 4 categories that we're going to talk about here. So we know about perfusion. It's the adequate delivery of oxygen and removal of waste products from the cells. When we have inadequate oxygen or inadequate removal of those waste products, we have hypoperfusion or shock. It's a breakdown in the system, and if this state lasts long enough, it can kill our patient, right? Enough cells will die because of a lack of oxygen getting to them, and then enough cells die, and organs die, and then your system or your patient dies, rather. So hypoperfusion can result in death. It's a bad thing. We need to know those, right? We learned those in the last chapter. We need to have a comfortable understanding with these. So you should be able to explain both of these well. All right, so we have 4 categories. These are general categories. And again, we'll have more specific categories that we'll be able to slot into these 4 general categories later. We have hypovolemic shock. So when somebody's in hypovolemic, right? Hypo is less than, below than normal. And volemic means volume. So we have a less than normal volume. And what we're talking about here is either blood or water. So if you bleed out, your volume of blood is lower than normal, and that can kill you. Obviously, I think the implications of not having blood in the system, hopefully that's obvious now, right? Can't carry oxygen, can't remove waste products. We can also have hypovolemic shock due to low water in the body, right? Being dehydrated. If you're dehydrated, we can also go into hypovolemic shock, less than normal volume of water. Distributive shock. This shock is concerned with blood vessels, right? Blood vessels basically distribute the oxygen throughout the body, and they take all the waste products and bring them back to the heart and lungs to be gotten off board there. So distributive shock is a problem with blood vessels. Mainly what the problem is they've lost tone, they've gotten too big, pressure drops, and so we have a problem getting the blood around the body, thus having deficits in oxygen and deficits in the ability to remove waste products, okay? So distributive shock has to do with blood vessels. Cardiogenic shock, obviously we know cardi, right? That means heart. Genic comes from the word genesis. And so the origin of the problem here is the heart. So if somebody has a big heart attack and a lot of cells and muscle tissue dies in, say, the left ventricle, and they're unable to circulate blood throughout the body, thus not getting oxygen to cells, not providing with a way to remove waste products, we go into shock. So cardiogenic shock, heart is the problem here. And then our last type is obstructive shock. So we have an obstruction somewhere. A good example of this is if there's a large clot or something in a pulmonary artery or vein, then we're not getting the blood back. We're not able to do the gas exchange if the blood is blocked from getting down to the alveoli. So we're not able to do the gas exchange. So somewhere there's an obstruction that is messing with our ability to have that gas exchange done well. So those are the 4 categories of shock. Now, there are different categories, right? But they all end up at the same place. And that place is cells aren't getting enough oxygen, not enough waste products are getting taken away. So the blood carries less oxygen because of that. And then cells die, organs die as your patient dies, all right? These are just different ways to get to the same place, okay? No matter what kind of shock or category of shock that patient might be in, the end result is always the same. Lack of oxygen or removal of waste products kills the cells. Cells die, organs die, then your patient dies, okay? So this is like if the end result is getting somewhere, these 4 things are just different ways to get there. So if the end result is going to Disney World, you know, if you went by a car and I went by a plane and somebody else went by a train and somebody else walked, right? The destination is still the same. We're just getting there by different ways, okay? So these are different ways to get to the same result, which is lack of oxygen to the cells, lack of waste products being taken away, cells die, organs die, your patient dies. Different ways to get to the same place. All right, compensation. All right, so we've talked about how things can go wrong. All right, now let's talk about how the body keeps us in that Goldilocks zone, or attempts to, and that's what compensation is, the body attempting to keep us in that Goldilocks zone where things are you know, not too hot, not too cold, you know, the bed's not too lumpy, it's not too soft or not too hard or too soft, it's just right. Things are just right there. So recognizing it. Whenever there's a problem with one of these systems, the body is going to attempt to compensate. And so we need to see what those signs are. Now, with compensated shock, the body is recognizing, excuse me, the body's recognizing that we're not getting enough oxygen to the cells, we're not removing enough waste products. So the body's going to attempt to do that. So think about it here. If the body recognizes that there's too much carbon dioxide in the blood and there's not enough, and the oxygen levels are too low, what are some things that the body could do to correct that? Okay, well, let's see. Well, one of the first things, excuse me, one of the first things that we're going to see, as we saw in those hypoxia videos, is mental status changes. The brain cells are very susceptible to change based on lack of oxygen or lack of sugar. So we'll see a slight mental status changes, right? We saw that guy have problems with thinking, very basic thinking, just naming cards, right, in that video. So we'll see slight mental status changes there. That'll be a sign of it. But then we'll see signs of compensation as well. So we'll see an increased heart rate, trying to get what blood we have around as best we can to all the cells and then back to the lungs to get rid of the waste products and pick up more oxygen. So we'll see an increased heart rate. We'll see an increased respiratory rate to try to get more of that waste products off board and then bring more oxygen on board there as well. We're also going to see delayed capillary refill time. Capillary refill, it's a simple concept. If you take your thumbnail or any of your fingernails and you press down on it, you'll see that it kind of becomes white. What you're doing there actually is pushing the blood out of the capillaries. Now, normally, when you let go of your thumbnail, it fills back up and kind of becomes pink, basically less than 2 seconds or less than the time it takes you to say capillary refill. Now, if we have a delay in that, that's a sign of an issue. If you'll remember back to our fight or flight responses, right? What happens to your GI system with the blood going to your GI system when we have a fight or flight response, right? Your body says, you know, we don't need to worry about digesting that cheeseburger right now. We need all of our blood going to things like our muscles and our lungs and things like that. We don't really need to be digesting stuff right now. So it shuts it down. It shunts blood to other places. Exact same thing is happening here. So our body's recognizing that we're not getting enough oxygen to the cells, not getting enough carbon dioxide off. So do we need blood here all the way at the end or out by our skin to stay alive? No, not really. So our body's going to shunt that blood away over towards our vital organs. So there's less going out here. So when we press on our thumbnail and then we see it takes longer than 2 seconds to refill back up, that is a sign that blood is being shunted away from things like our skin and our like our phalanges all the way out the end of our extremities. That's a sign that the body is shunting blood to more important places: the brain, the heart, the lungs, the kidneys, those kind of things. Right. So we're going to see that. That's a sign that the body is working to keep blood to the vital organs there. Because the blood is away from the skin, it gets pale, it gets cold, right? Our blood warms our skin here. So it gets pale and it gets cold. It's also going to become clammy. You know, we're going to see people sweating a lot, and it can be profusely sweating. So like when you've seen that in movies, they've actually done a decent job when somebody is, you know, some maybe war movie or whatever it might be, where somebody may be shot or has been bleeding a lot, and they look pale and they look sweaty and they're like, oh, I'm so cold and thirsty, right? All that's true. All that's true. And that'll happen. So if you actually see that, that's not a bad job that they've done. They've actually taken time to kind of understand what the body is doing to show it. So we need to be able to see these things or recognize these things: the mental status changes, increased heart and respiratory rates, the delayed cap refill time, and then the condition of the skin: sweaty, pale, cool, clammy. These are all signs that the body is compensating, trying to perfuse our vital organs, again, brain, heart, lungs, kidneys, etc. on there. And that it's a sign that it's taking it seriously. And it's like, all right, I don't really need blood out here in my skin or in my fingertips to do that. I need it other places to keep us alive. So these are all signs of compensated shock, and it's something that we should be able to recognize easily. All right, pathophys of some other systems here. We actually talked about fluid balance with the plasma oncotic pressure and the hydrostatic pressure. Right, we've got to have that right amount of fluid balance, right amount of water in and around the cells, right amount of water in the bloodstream as well. Body's about 60% water, and there's the breakdown of where the water is. Most of the fluid, 70% of it, is intracellular fluid. That's in the cells. 5%, which is, this has kind of always been a surprising number to me. Only 5% is intravascular, so inside the bloodstream. And then 25% is interstitial, of waters in the interstitial spaces. This is the spaces that's between cells and tissues and things like that. So that's where our fluid balance is there. So we know that the kidneys they're a primary organ in the renal system, and they play a major part in maintaining our fluid balances and eliminating excess fluids. So, you know, when you get thirsty, when your body tells you that you're thirsty, it's your brain recognizing, hey, we need some more water on board here. So let's get some of that in there. And then obviously the kidneys do the job. If we have too much fluid, probably see somebody pee more if they've got too much fluid. The kidneys are getting rid of that excess fluid there, trying to keep that balance in that Goldilocks zone just right. So there's that we see there the plasma oncotic pressure, and then we also have permeability. It's got to be controlled to a level where not too much fluid is leaking out of the cells or not too much fluid is leaking out of capillaries. There, it's got to be the right amount of leakiness. Again, Goldilocks zone, right? Just right there. So we can have disruptions in the fluid balance. Obviously, if somebody's dehydrated, that's a severe disruption in the fluid balance. We like to keep it just right. But if we get to dehydration, as we talked about earlier, we've got to have the right amount of water in the cells. And if there's not the right amount of water, it can't do its job, starts to malfunction. And eventually, if it dries out enough, it dies. So fluid loss, it's a decrease in the total water volume throughout the body. And we can see fluid loss there. We can see poor fluid distribution. So let's say we've got a liver problem, we're not making that large protein albumin, then the fluid balance is off because those proteins aren't sucking water from interstitial spaces back into the bloodstream. And so all that water stays out in the spaces outside the bloodstream, all that extra. And then we'll start to get edema, swelling. Water's not going where it needs to go. So we get the edema. And that is, it's like it says here, it's water, too much water in some parts of the body. And normally, as we said, where we're going to see that is in the lower legs. We can also see it in the arms too, past the elbows, down by the wrists and hands. You can see swelling there. And it's called edema. We'll need to know what that is. Here's a couple pictures of edema. This person we can see here has very swollen feet. It's difficult to see the malleolus on either foot, either medial malleolus there. We can see right at the edge of the foot, just before the toes, right in here, how it goes into the toes, but there's only so much that it can do. And then we have this kind of bump here at the end of the foot, but right before the toes, we can see how much swelling that is there. So that's a good example of swelling and edema. Here on the foot on the left side of the page, or both of them, you can actually see right by the toes that bump where it swells up. Now on this foot on the right hand side of the page, you can see these 4 pits. This is called pitting edema. Somebody has pressed their 4 fingers down into this person's foot, has made these little pits, and they're just basically pushing water out of the way to make these pits, and eventually these kind of fill back up. The water fills back up in the tissues underneath those, and those kind of go away. Here's another picture of pitting edema. In the first one, in the top picture, you can see someone pressing down on this child's feet, and then they take their fingers away, and you can see the pits there. So this person has, this child obviously has some edema going there on their lower extremities. All right, let's talk about the nervous system and how we can disrupt that. As we know, the brain and spinal cord, they're protected well by the skull and the spinal column there. So we'll need to know a couple things here. The brain and spinal cord, they have several protective layers. These are kind of tough fibrous layers. These are called the meninges. When those become infected, you have what's called meningitis. So it's a protective layer around the brain and spinal cord there. And when those are infected, we have what's called meningitis. And then we have a layer of fluid. It's called cerebrospinal fluid, or CSF. This is a fluid that surrounds and bathes the brain and spinal cord, and it offers a level of protection. It also bathes it in nutrients, things, kind of takes care of it there. Those things help protect the brain inside the spinal column and inside the skull. Even though they're well protected, obviously they're still subject to damage through trauma or disease. You can only do so much to protect parts of the human body. So when we have dysfunction, one of the main ways is through trauma. So you have head trauma, you have spinal trauma. Some ways we can get that, where there's major forces being applied to the body, are motor vehicle collisions, particularly when patients are not belted in, or if there's rollovers, like tremendous forces can be applied to the body. And so major traumas can result, traumas to the head, neck, spine, rest of the body. Obviously falls, going downstairs or falling off a ladder or from any kind of height, usually it's greater than 6 feet or 10 feet. For kids, about 18 feet or so for adults, like that kind of stuff can result in major trauma. That's a long ways to fall. A lot of force applied to the body when you hit when you suddenly decelerate, when you hit the ground. Other things that can happen are diving accidents. Somebody dives into a shallow pool and they have a compression injury when they hit the bottom of the pool with like the very top of their head and compresses their spine. That obviously places a lot of force on the spine, and we can have trauma there. Other dysfunctions are medical dysfunctions. So we can have strokes. Obviously, lack of blood supply. If a artery in the brain is either occluded, it's blocked, or if it's burst, an aneurysm has occurred, a bubbling, basically of a weakened wall of an artery kind of bubbles out and then bursts. Those can result in strokes. We can have infection. We can have meningitis, which is the meninges being infected, or we can have the brain itself being infected, which is encephalitis. You should know the difference between those two. We can have diseases like ALS, which is Lou Gehrig's disease, which is basically a breakdown of the nervous system. A patient that gets that at the end, before they die, the nerves have broken down to the point where the brain basically can't send signals out to their body. And so you see these people in the last couple of years of their lives in wheelchairs, basically paralyzed. They can't move anything. They're on breathing apparatus and whatnot there. So they can't speak, things like that. They basically lose the ability to send signals out to their body to do anything. MS is another example of that as well. And then we can have low blood sugar. As we said earlier, the brain is really susceptible to changes when it doesn't have enough oxygen or glucose. So when they're hypoglycemic, which means low on blood sugar, we can see dysfunction of the nervous system there. So those are some ways for that to happen. All right, we got the endocrine system. As we know, that's the system that secretes hormones. We have several organs throughout the body that do that, and these hormones, they regulate body functions. And so generally the tendency here is for the endocrine system, for whatever organ we might be talking about in the endocrine system, whether it's like the pancreas or the thyroid, parathyroid, things like that, that either too much or too little hormone is being produced. So those are some of the major glands that we see there. So again, the problem is we're either getting too much hormone or too little hormone. So it's either way too much or it's way too little. We're not in that Goldilocks zone with the hormones. It's not just right. It's too much or it's too little. Those are the problems there. So it's an organ or gland problem. A lot of times it's present at birth, or it's the result of having an illness. So Graves' disease is a type of dysfunction, endocrine system dysfunction there. We have too many thyroid hormones. These people have problems regulating their heart rate and their temperature as well. So they run hot and their heart tends to beat too quickly. Not enough hormones. An example of that could be diabetes, where the pancreas isn't producing enough insulin to let the glucose get into the cells. Right? We don't have that Goldilocks zone. We've got enough sugar, but not enough insulin in this case to actually get the sugar into the cells. So again, endocrine system problems, too much or too little hormones. All right, digestive system problems. Digestive system, obviously, the job here, the digestive system, it allows food and nutrients into the food, water, and nutrients into the body and get it into the systems. The major organs here, we got the esophagus, the stomach, the intestines, and then we have lots of accessory organs too. We've got the pancreas, we've got the liver, we've got the gallbladder. So we've got different organs here associated with these digestive system. So one of the bigger issues that we can have with the digestive system is the impact is on whether or not we can get water into the system or nutrients into the system. So our water balance could be off because of our digestive system, or our nutrient balance. Maybe we're not getting enough electrolytes, vitamins, things like that into our body for jobs and places to get done. So that's what that's what can happen there. Another problem can be GI bleeding, gastrointestinal bleeding. So if we're bleeding somewhere, that means oxygen's not getting to the cells somewhere, right? And so we can have dysfunction of the organs because of bleeding there. It can be slow, it can be chronic. If it's lower GI bleeding, I promise you'll never forget the smell once you smell it. And it can be a lot. It can be a lot too. So it can absolutely be a life-threatening situation. So vomiting and diarrhea, they're the most common types of digestive dysfunction. Our big thing, a big takeaway from vomiting and diarrhea is that it can result in severe dehydration very quickly. It can also result in malnutrition. So if somebody, there are certain diseases out there that cause you to diarrhea a lot or vomit a lot, and that can result in severe dehydration pretty quickly. There are other conditions out there like bulimia, for example, when a person that's when a person eats something, and because they have um, mental health struggles with the perception of their body, they may, after they eat, they may vomit what they eat out. And so they don't gain weight. In doing that, not only are they losing water, but they're not able to get the nutrients from their food. And so they suffer from malnutrition. So we're not getting the electrolytes, the vitamins, all of the things necessary from nutrition. They're not getting all that stuff into their body. And so we're going to start seeing dysfunction in places with our cells because we don't have those types of things. But again, vomiting, diarrhea is the most common type of digestive dysfunction. The immune system, we know what that is, responsible for fighting infection. It's our first line of defense there against outside invaders. It responds to them by identifying them, marking them, producing specific types of cells that will attack that specifically, and they destroy them there. Thank goodness we have that. A hypersensitivity or allergic reaction is a problem with our immune system. It is basically an overreaction to things happening in our bodies, right? Like there's no reason that cat dander or a peanut, should kill somebody, things like that. So allergic reactions, the body does not like certain foods, drugs, other substances, and they have an exaggerated immune response. They see this invader in the body, they think it's an invader, and in the process of destroying these invaders, there's chemicals released. They're called histamines, and they produce lots of swelling and edema. It can, because of that, also we get our permeability goes up, so it can result in a lot of swelling. We can get loss of tone as well, which can result in a rapid loss in blood pressure because of loss of blood vessel tone. They just get too big, and the blood pressure drops dangerously, and it can be life-threatening. All right, there's our chapter there very quickly. Again, this is to supplement what we've done in class, your reading, the notes, the videos, everything that we've done there. So please watch over this, study up for the Chapter 7 test. If you have any questions, please let me know. All right, guys, we'll see you next time.